Now, there are many situations where we are interested not in the rotation of the whole body, but in the motion of a particular point on the body. And what we're going to do now is come up with a way of relating the rotational quantities, so the angular displacement, velocity, and acceleration. We're going to come up with a way to relate those to the linear motion or translational motion of a single point on the rotating body. So if we think about this point, this black dot here, on some rotating wheel or disk, then its speed is the distance that it travels per unit time. And so if we look at it moving from here to here, then the distance that it's moved through, if that angle is theta, the distance that this point is moved through, well, that's the arc length, right? And so the distance is just going to be the radius times the angle, because that's how we define the arc length. So remember that that the angle is equal to the arc length, or the distance in this case that the object's moved, divided by the radius. So the radius here being the distance that it is away from the axis at the center. And so if we want to work out how far it's gone, the distance is just going to be equal to r times theta. The linear speed of this thing is going to therefore be the distance that it's traveled divided by the time that it's traveled. So the velocity is the distance over time, and that's equal to r theta over time. The radius isn't changing. It's not getting further away or closer to the axis of rotation. And so that's just v is going to be equal to r times the delta theta over delta t, which is r times omega. So just as d is r times theta, v is r times omega. So that shows the relationship between the linear speed of this object as it moves around in a circle to the angular speed of the object itself. We just multiply the angular speed by r to get the linear speed. So calculate your linear speed if you're standing 3 meters from the center of a turntable spinning at an angular speed of 0.5 radians per second. Well, we use the fact that v is equal to r times omega, which is, well, r is 3 meters because we're standing 3 meters away from the center, and omega is 0.5 radians per second. So that's just 3 times 0.5, which is 1.5. And we've worked out a linear speed, so that's meters per second. Remember, the reason why the unit radian is dropped out of it is because the unit radian is really the ratio between a distance and another distance, the arc length and the radius, and so the unit meters cancels there, so the radian is really a unitless in terms of physics. We can do the same thing for linear acceleration and angular acceleration. So the linear acceleration, a, is equal to the rate of change of speed, rate of change of linear speed. This is kind of problematic because the linear acceleration is a vector, but if we think of this, if we make this change very, very small, then we can call it the tangential acceleration. But for now, we'll just we'll kind of sidestep that. We'll ignore that. This is basically the acceleration of the object as it moves around the circle. So what we need to do is make this this change happen over a very short time. And those of you that are studying calculus at the moment, you'll get what I mean by this. If not, we'll just ignore it for now. What we're working out is basically how quickly the speed of this object as it moves in a circle is changing. So the change in linear speed over the change in time, that's going to be equal to r times the change in angular speed over the change in time, because r omega is equal to v, right? So r times the change in omega should be equal to the change in v. So this is just equal to r alpha, where alpha is the angular acceleration. So the linear equations, v is change in distance over change in time. A is change in velocity over change in time. That's what we studied last year. The rotational equations, omega is the change in angular displacement over the change in time. Alpha is the change in angular velocity over the change in time. If we want to convert, then the distance is equal to r theta, where that's the distance that the object or the point that we're interested in away from the center, that's r, and theta is the angular displacement of the rigid body. V is r omega and a is r alpha. So we can, if we know the angular quantities of the object, then we can easily convert those to the linear quantities if we just know how far the point that we're interested in is away from the axis or the center of rotation. Okay, so that's kind of relating what we did last year to what we did this year. What we're going to do next is just apply these kinematic equations for rotational motion to a number of problems so we can get the hang of that.